All right, so last time we started our discussion on open channel transitions. So up till this point, we had talked about uniform flow. When we have changes in the geometry of channel or changes in the bottom elevation of the channel, we found that there are going to be changes in the way the flow responds, particularly how the depth and the velocity change over the channel. So we went through an example problem of a transition involving a rise in the bottom elevation of the channel. I showed you the case where we had subcritical flow transitioning into subcritical flow at the crest of this transition. And then towards the end of class last time, I gave you an example problem to work on where you were to find the height of the ridge needed to produce the critical depth. So this was the problem from the end of the last lecture. You were to find the height of this transition needed to produce the critical depth at the crest of the bump and would produce a supercritical flow regime downstream. So just a show of hands, who completed the first problem from the in-class assignment last time? Raise your hands high, please. Okay, most of you. Who completed the second problem? Who completed the third problem? Okay, so I'm going to give you about 10 minutes to finish this up. If you've already finished, then you can start working on the homework. We will reconvene in about 10 minutes, and I'll go over this problem, and then we're going to transition to our next subject, okay? All right, so quick show of hands again. Who has finished all three problems? Okay, see a good number of hands here. So let's just quickly review. I'm not going to give the full answers, but let's walk through how you would solve these different problems. So for the first problem, finding the critical depth, how did you do this? What equation did you use here to find the critical depth? Froude number. What did you set the Froude number equal to? 1. Very good. So critical depth is characterized by the Froude number being equal to 1. So remember, the Froude number was given by the velocity times the square root of the top width divided by the square root of the acceleration due to gravity times the cross-sectional area. We can re-express the velocity in terms of the discharge. So we have Q over A times the square root of T divided by the square root of GA. So we can take this expression and square both sides just to make it easier to work with. So we end up with 1 squared is equal to, this will be Q over A times the square root of T divided by the square root of GA. And square both these sides, and we get that this is equal to Q squared over A squared times T divided by GA. And what's the last piece we need here to be able to compute the critical depth? What do we need to do? So I have expressions for, I think I heard someone say it. Very good. So the cross-sectional area will be equal to B times H. We'll end up with 1 is equal to Q squared over B times HC for the critical depth. Top width is equal to the bottom width, so that's just B times, oh, this whole thing is squared, by the way, times G times BHC. Turns out that you can rearrange this to get a closed form expression for HC. Critical depth, it'll be equal to about Q squared over GB squared all to the 1/3 power. So for a rectangular channel, you can get an explicit expression for the critical depth. Okay, very good. Next, to find delta Z max, how did you compute the height of the bump needed to create a transition through the critical depth? What equation did you apply here? Energy equation from 1 to 2. So we'll have H1 plus C1 plus U1 squared over 2G is equal to HC plus Z2 plus UC squared over 2G. We can take Z2 minus Z1 is equal to delta Z max. So we get H1 plus U1 squared over 2G is equal to delta Z max plus HC plus UC squared over 2G. And then we can rearrange explicitly for delta Z max. We know all of the other variables because we have the critical depth. We'll have H1 minus HC plus U1 squared over 2G minus UC squared over 2G. And we can compute this velocity from the discharge and the critical depth. All right, finally, find the supercritical depth at the downstream end. So what was the key point or the key fact that you needed to solve this problem? I mentioned it last time in class. Right, so we're assuming no energy losses over this transition. It's a short distance, so the frictional losses will be small, and it's a smooth bump, so we won't get any kind of minor losses associated with the bump. So we have that E1, the specific energy at point 1 is equal to E3, the specific energy at point 3. From E1, we have that E1 is equal to H1 plus U1 squared over 2G. E3 is equal to H3 plus U3 squared over 2G. So if you rearrange this, you should be able to get an expression for H3 in the form of a cubic polynomial. You can solve that cubic polynomial to figure out the supercritical depth downstream of the bump. All right, any questions on these three problems? So yes.
You go back to the equation on number 2.
So this is just the energy equation. And I've just rearranged it for the height of the transition. So on homework 7, there will be different problems involving channel transitions. Up till now in class, we've looked at just transitions in the bottom elevation of the channel. On homework 7, there will also be transitions in the width of the channel as well. So make sure that you understand how to do these transition problems. The same principle applies. The same basic method is going to apply. It's just going to be slightly different on the homework, where you're experiencing changes in the channel geometry as opposed to just the bottom elevation. All right, any questions on this problem before we move on? All right, well, go ahead and get started on homework 7 today. Again, that's due on Friday. It'll be similar to this example we've done in class. Today, I want to move on. We're going to talk a bit more about transitions between subcritical and supercritical to subcritical. And specifically, we're going to be talking about hydraulic jumps, which you observed in lab 4. So when does a hydraulic jump occur? Very good. So a hydraulic jump occurs anytime that you have a transition from supercritical flow to subcritical. So that is what characterizes a hydraulic jump. It's a transition from supercritical flow at the upstream end to subcritical flow at the downstream end. So let me give you a quick overview of hydraulic jumps, show you some pictures. So hydraulic jumps, again, what characterizes them is it's a transition from supercritical to subcritical flow. One familiar case of a hydraulic jump that you may see every day but not recognize it is flow from a faucet into a sink. So when that flow from the faucet hits the bottom of your sink basin, it'll start out with a very rapid flow that proceeds outwards from the point of contact until you get a transition to subcritical flow downstream. So even in this very mundane case, you can often find a hydraulic jump. So one important feature of hydraulic jumps that we're going to talk about today is that you will typically see these turbulent eddies that form inside the jump. Now the severity of these eddies depends on the Froude number essentially of the flow coming into the hydraulic jump. But this is where you see a lot of energy dissipation within the hydraulic jump. So hydraulic jumps, typically you will get a large amount of energy dissipation as these turbulent eddies dissipate kinetic energy as it transitions into subcritical flow. So we'll talk a little bit about those eddies and how to characterize those energy losses today. So some examples of where you might find hydraulic jumps in terms of hydraulic control infrastructure. Sluice gates, so these are, you can sometimes find these in certain types of dams. You'll have a transition from supercritical to subcritical flow. And again, you can see that energy dissipation in the hydraulic jump. Another place you'll find hydraulic jumps out in the real world is at the foot of spillways on dams. So here we have supercritical flow coming down this spillway. It encounters a hydraulic jump. And again, you'll get kind of that rotational turbulent eddies in the hydraulic jump and then subcritical flow downstream. So this is what a hydraulic jump would look like in real life. So often when we're designing hydraulic infrastructure, we will be interested in inducing hydraulic jumps. So I'll talk about why we might want to do this a little bit later on. But there are fixtures that we can put in to actually assist with the formation of a hydraulic jump. So these are called energy dissipators. You'll see these both in large scale hydraulic infrastructure like in dams, as well as small scale stormwater infrastructure. So these help assist the formation of a hydraulic jump. We'll go through the physics exactly of how that happens today. Here's an example in stormwater specifically. So we have these energy dissipators at the outlet of a culvert. Those energy dissipators will help assist that transition from supercritical to subcritical flow. And again, hydraulic jumps, they're going to depend a lot on the relative velocity of the water coming into the hydraulic jump versus the velocity exiting the jump. So you may get very subtle hydraulic jumps when your upstream Froude number is close to 1. As that Froude number increases, the hydraulic jump will become more and more dramatic. So there's not just a single kind of hydraulic jump, but rather the magnitude of that hydraulic jump is going to depend on the upstream Froude number. So let's talk a bit about how to analyze hydraulic jumps. Today, specifically, I'm going to talk about how to determine, well, first, how to analyze hydraulic jumps, and second, how to determine the sequent depth and velocity downstream of a hydraulic jump, given some information about the flow entering the hydraulic jump. So we're going to look at how to determine the sequent depth and velocity downstream of a hydraulic jump. This is particularly important if we're designing a spillway or some other kind of stormwater infrastructure in which we want to know what the depth of water is going to be and what the velocity is going to be downstream of that transition, specifically if we want to design the hydraulic jump to reduce that depth and velocity below some threshold value. So let's go ahead and analyze a hydraulic jump. By the way, before I get into this, why might we be interested in creating a hydraulic jump? So why might we be interested in installing energy dissipators to assist with the formation of a hydraulic jump? Yeah, so when we transition from supercritical to subcritical flow, what's going to happen to the velocity of the water? It's going to decrease, right? So typically, if we're installing like a culvert that is going to carry water into some natural stream bed, we want to reduce erosion as much as possible. So erosion is caused by very rapid flows typically. So typically the larger the velocity, the more erosion you'll get. So we often want to induce a hydraulic jump to limit erosion or limit other damage to the channel downstream. So again, in analyzing and designing these hydraulic jumps, we want to be able to determine what the depth and velocity are going to be downstream of the jump. So let's take a look at a hydraulic jump. I'm going to draw a control volume around our hydraulic jump. And let's say we have some depth and some velocity upstream. So let's say we have some velocity U1, some depth, so I'll call H1. And we want to know what the velocity, what the velocity and depth are downstream of our hydraulic jump. So how can we go about analyzing this system and computing what the downstream velocity and depth are going to be? What equation do you think we're going to use here? Wrong. Wrong. So I think I may have given you too much confidence in the energy equation. Why might it not be a good idea to use the energy equation here?
Oh, energy is wrong.
Very good. So like I mentioned earlier, inside of this hydraulic jump, there are going to be these turbulent eddies that are dissipating energy. The problem is that we don't really have any analytical way of estimating what the energy losses are going to be inside the jump. So typically we won't know how much energy is lost in the hydraulic jump until we know what the velocity and depth are on the upstream and downstream ends. So we actually can't use the energy equation to compute the sequent depth and velocity in a hydraulic jump. So this is one of the few times in this class where the energy equation is not going to help us, at least not directly. So what else can we use here to try to figure out what the depth and velocity are going to be at the downstream end? What other tools do we have at our disposal? A model? So a model based on,
Or there may be a simulation or like making it, constructing like a small little channel and a small little bump or something. And that's like the depth of the below.
okay, so actually, yeah, if did you look at how like hydraulic similitude and fluid mechanics? Is that something you covered? So that is one approach you could take, is you could build a scale model of this hydraulic jump and try to scale it up. Let's try to think of techniques that aren't going to require, building a physical device, what other mathematical tools do we have at our disposal? What equations do we have? Yes. Yes, so that is true. So we have continuity. So that might be useful. That won't give us enough information because we have two unknowns here, U2 and H2, and continuity will only resolve one of those. So we have the energy equation, we have continuity. What else do we have? Yes?
Maybe something relating to the conversion of potential and kinetic energy.
So it'll be related to energy. What other so what other equation did I give you at the beginning of class that from which we derived the energy equation? Yes? So we will end up using the Froude number. Well, not directly. So what's kind of our other fundamental equation that we have in this class?
Momentum.
Momentum, very good. So we can apply conservation of momentum, or we can apply a force balance to try to analyze the different forces acting on this control volume. And from that, we should be able to get another equation that'll help us resolve this upstream and downstream depth and velocity. So let's go ahead and apply Newton's second law. So we have that the sum of forces is equal to the rate of change of momentum. So that's d of mu by dt. And let's think about the forces that'll be acting on this control volume. So this is a horizontal channel, and it's going to take place over a short distance. So what are the forces that will be acting on this control volume? Gravity. So we'll have gravity acting in the y direction. So this is mg. That's for the weight of the water. What is the component of the gravitational force in the direction of flow? So it'll be mg s naught or mg sine theta. Because this is a horizontal channel, the bottom slope will be 0. So this whole term can go away. Okay, what other forces do we have acting on this control volume? Friction. So there will be a frictional force acting opposite to the direction of flow. I'll call that F sub F. In this case, though, the actual distance here is pretty small. So if you remember back to those pictures, the hydraulic jump can occur over a fairly small distance. So we're going to assume that this frictional force is roughly equal to 0. It's going to be very small. What other force do we have acting on this control volume? Pressure. Okay, so we have the hydrostatic pressure of the water itself. And it's acting on both sides. So we will have the hydrostatic pressure at the upstream end. So this will be given by rho times g times the centroidal height times the area at the upstream end. So let me just quickly go through where this comes from. So this is something you looked at in fluid mechanics. So remember that for the hydrostatic pressure, the pressure at some distance h from the surface is going to be rho times g times h. Here we're talking about the h being the distance from the surface. So H would be, this distance here. So the force is what you get if you integrate this pressure over the entire depth and multiply by the area. So this will be our force is going to be given by the integral from H to 0. Actually, let me so we're going to be, let's say this whole height here is H. We're going to go from H all the way to the bottom. So this is going to be rho times G times H times dA. You know what? Let me call this big H because this is incorrect notation here. So note that this dA, this is equal to, we're just basically taking these strips of the channel and adding them up. So this dA is going to be rho times G times H times the width, which I'm going to call T, it's a function of H, times DH. And when you perform this integral, so I can take out the rho G, becomes H TH DH. This would give us rho times G times the centroidal depth times the area. Note that this expression THDH, this would, well, this whole thing would be the centroid times the area. So just from the definition of the centroid. So when I'm talking about, when I'm saying the centroid here, this is this distance here from the top. So that's our expression for the hydrostatic force. So this should be a review of fluid mechanics, but I'll have some extra material in the typed notes if you need a little more time with this. So in short, the force, the hydrostatic force is equal to the specific weight, that's rho times G, times the centroidal depth from the surface to the centroid of the water, times the cross-sectional area. And that comes from evaluating this integral here. So at the upstream end, we have that the hydrostatic force is given by rho times G times the centroidal depth at the upstream end times the cross-sectional area at the upstream end. Downstream, we have that the hydrostatic force is equal to rho times G times the centroidal depth at the downstream end times the cross-sectional area at the downstream end. So quiz, is the hydrostatic force at the upstream end the same as the hydrostatic force at the downstream end? No. Which is larger? Right, the downstream end has a larger depth, therefore it's going to have a larger hydrostatic force. That means that the sum of forces is not equal to 0. There will be some momentum flux through the control volume. It also means that if you apply a analysis of the moments, are these two forces here collinear? No. So that's actually where this rotational motion comes from. So the centroid of this triangle will be higher than the centroid of this triangle. That means the forces are not collinear, and that's what causes these rotational eddies. So I'll draw the centroid of this triangle will be, well, it'll be a bit lower than this, but it'll be somewhere like down here. The centroid of this triangle will be somewhere like here. So you'll actually get two forces acting on the control volume that are not collinear. That's what causes those rotations. All right, so let's go ahead and take a closer look at our force balance. We have that the sum of forces is equal to the time rate of change of momentum. As I mentioned, this rate of change of momentum is not going to be equal to 0 because the sum of forces is not equal to 0. So if you remember from our earlier discussion and from Reynolds transport theorem, the net rate of change of momentum is equal to the mass times the time rate of change of the velocity plus the mass flux out, sorry, the momentum flux out minus the momentum flux in. So these momentum flux terms, this is the mass flow rate times the velocity. So the momentum flux will be the momentum transfer out of the system minus the momentum transfer into the system. So this here is our momentum flux. We're assuming that the system is at steady state, so this time rate of change in momentum is equal to 0. All right, the sum of forces, as we talked about earlier, this is going to be rho times g times the centroidal depth at the upstream end times the cross-sectional area at the upstream end minus rho times g times the centroidal depth at the downstream end times the cross-sectional area at the downstream end. We can also simplify this expression so that we don't, well, there's another way that we can express this mass flow rate in terms of the other variables that we might know. So what is the mass flow rate equal to in terms of other variables that we know? Q times density, very good. So the mass flow rate in is equal to the mass flow rate out is equal to the density of water times the flow rate. So let's equate these two sides here. We'll end up with rho times G times H bar 1 times A1 minus H bar 2 times A2 is equal to rho times Q times U2 minus U1. And you'll notice here that the density can be divided out. And we end up with the following expression for our momentum balance. I'm going to flip the size just because I like writing it this way better. Q times U2 minus U1 is equal to G times quantity H bar 1, A1 minus H bar 2, A2. So this is our momentum balance. Around our hydraulic jump. And if we take this and we combine it with our continuity equation, we should be able to compute both the velocity and the depth downstream of our jump, given the depth and velocity coming into it. Are there any questions on how I derive this momentum balance. Yes,
Can you find us why the mass flow rate is equal to density times the flow rate?
so Q is the volumetric flow rate. That is in units of something like cubic meters per second. The density is in units of something like kilograms per cubic meter. So if you take the density and multiply it by the volumetric flow rate, you'll get kilograms per second. That would be the mass flow rate. Okay, good question. Any other questions on this derivation? Yes.
So for thermal forces, just like the horizontal, it's like what happens to the gravity?
Yeah, we're assuming that if we're looking at like a stilling basin or something like that, it'll typically be a roughly horizontal section. So we're just neglecting the gravity force because it's a horizontal channel. For the frictional force, we're neglecting it because it's a very short distance. So you won't have much length to accumulate those frictional losses. Good question. Any other questions before we move on to an example? All right, well, let's do an example. And I'm gonna design well, we're going to analyze a hydraulic jump within a stilling basin. So let's consider a stilling basin. So this would typically be at the downstream end of a dam. So let's consider a stilling basin. It's going to consist of a rectangular channel. With a bottom width B equal to 10 meters. There's a discharge of 100 cubic meters per second coming into our stilling basin. So this is Q equal to 100 cubic meters per second. And the depth upstream of the hydraulic jump, the depth at the upstream end of our hydraulic jump is going to be H1 is equal to 0.6 meters. And what I want to do is I want to compute the depth H2 downstream of the jump. And let's draw a quick schematic here. We have a horizontal channel, going to be rectangular. We have some flow entering at a discharge of Q equal to 100 cubic meters per second. And a depth of H1 is equal to 0.6 meters. We're going to encounter a hydraulic jump. And we want to compute that depth H2 downstream of the hydraulic jump. So we can apply our momentum balance. We have from the equation we just derived, the flow rate Q times quantity U2 minus U1, that's the velocity out minus the velocity in, is equal to G times quantity H bar 1, that's the centroidal height, times A1, the cross-sectional area at the upstream end, minus H2, the centroidal height at the downstream end times A2, the cross-sectional area at the downstream end. We don't know the velocities, so let's re-express these velocities in terms of the discharge. So we'll have Q times quantity. U2 will be discharge divided by the cross-sectional area. How can we express the cross-sectional area in terms of the variables we know? Okay, B times H2. And same thing for U1, this will be Q divided by B, the bottom width, times H1. Okay, so for the right-hand side, we need the centroid or the centroidal height of our channel. For a rectangular channel, what will the centroidal height be? Sorry, I couldn't hear. Very good. So it'll be H1/2. So we have a rectangular channel. And we want the distance from the surface to the centroid of this rectangle. That distance to the centroid, because it's a rectangle, is just going to be h divided by 2. Yes.
But when you're just doing it with like the hydrostatic though, that the centroid is actually lower because it was a triangle with like 2/3.
That was the centroid of the triangle. This is just the centroid of the channel. So when you're when you're analyzing the balance of moments, then you would need that centroid of the force triangle or pressure triangle. Here, it's just the centroid of the channel itself. A good question. Are there other questions about this? So I hear some murmurs. So this centroid that I'm talking about here is different from the centroid of the pressure triangle. So if you think back to statics, if you're applying a not a momentum balance, if you're applying a balance of moments, that's when you'll use the centroid of the pressure distribution, which will, for a triangle, it'll be, you know, a third up from the base of the triangle. This here is for computing the centroid of the channel itself, and that comes from this integral here. So I would review this if it's still hazy from fluid mechanics, and I can post again the typed notes with this derivation, but this expression here is basically giving you the centroid times the area, just from the definition of the centroid. Centroid of the channel times the area of the channel. Yes. It'll depend on the shape of the channel. So for a triangular channel, for instance, let's say you have a triangular channel like this. Pretend this is a symmetric triangle. What would be the distance to the centroid of this channel? 1/3, very good. So for a triangular channel, this would be h divided by 3. Yes.
How do you whether H 1/3 the top or 2/3 the bottom?
From the way that we set up our expression for the force, it's from the top. Yeah, good question. Because when we were doing that integral, we did the integral from the top to the bottom. All right, good questions. So let's go ahead and finish up here. So for a rectangular channel, this centroidal height will be h1/2. This is times A1 is going to be the bottom width times H1 minus H2/2 times B times H2. Let's multiply through this discharge, so we'll end up with Q squared over BH2 minus Q squared over BH1 is equal to G. We can pull out this B here, so we'll have GB times quantity H1 squared over 2 minus H2 squared over 2. At this point, we can go ahead and start substituting in numbers. So for the discharge, this was 100 cubic meters per second. So we'll have 100 squared. Our width is 10 meters. We don't know H2 yet, so I'm going to leave it as a variable. We'll take this expression minus 100 squared divided by 10 times H1 is 0.6. Is going to be equal to 9.81 times the width of the channel, which is 10 meters, times quantity 0.6 squared divided by 2 minus H2, which is unknown, squared divided by 2. We evaluate this expression, we should get 1,000 divided by H2 minus 1,667 is equal to, this first term here will end up being 17.66. And then this last term here will be negative 49.05 H2 squared. So if we multiply through by H2, we will end up with a cubic polynomial. We will get 49.05 times H2 cubed minus 1,685 H2 plus 1,000 is equal to 0. And if we want to solve for the depth downstream of the jump, all we have to do is find the roots of this polynomial. To do that, I'm going to use, I'm going to graph it. Again, Excel is not the best tool for this. So let's go ahead and graph this function. We'll have 49.05 times x cubed minus 1,685 times x plus 1,000. And you'll see that we have one negative root at negative 6.13. We'll have two positive roots, one at 0.6 and the other at 5.54. So what is the correct answer for H2? 5.54. How do we know that? Very good. So the larger root corresponds to subcritical flow. The smaller root corresponds to supercritical flow. And you'll note here that this root is exactly the same as H1. So this is just the supercritical depth. So our answer is H2 is equal to 5.54 meters. So that's quite a big jump. We're going from less than a meter, about half of a meter, to 5.54 meters. That's what, like 16, 17 feet? So pretty big jump. All right. So my next question for you is, there's probably a lot of energy loss in this jump, given how much the depth increases, how can we go about computing the energy loss through our hydraulic jump? Don't be afraid. Energy equation, very good. Okay, so we can compute the energy loss by applying the energy equation now that we know the downstream depth. So how can we compute the energy loss? Apply the energy equation. So going from the upstream to the downstream end, we have H1 plus U1 squared over 2G is equal to H2 plus U2 squared over 2G plus the head loss due to that hydraulic jump. H1 is equal to 0.6. This expression here will have Q squared over 2 times G times B squared H1 squared is going to be equal to 5.54 plus Q squared divided by 2 times G times B squared H2 squared plus the head loss. We plug in numbers, we'll get 0.6 plus 100 squared divided by 2 times 9.81 times 10 squared times 0.6 squared. This is equal to 5.54 plus 100 squared divided by 2 times 9.81 times 10 squared times 5.54 squared plus the head loss. We evaluate this expression here. This will end up being about 14.16. This expression here will be about 0.166. So note here that if we're looking at the energy upstream and downstream, this here represents kind of the component that's in the potential energy, 0.6. This here represents the component of the energy that's in the kinetic energy, so that's 14.16. So most of the energy upstream is in the kinetic component. Downstream, we have potential energy is about 5.54 meters. Kinetic is 0.16. So supercritical, most of the energy is in the kinetic energy. Subcritical, most is in the potential energy. So let's go ahead and rearrange this for the head loss in the jump. We have that 0.6 plus 14.16 is equal to 5.54 plus 0.166 plus the head loss. And if you rearrange this for the head loss, you should get the head loss is about 9.05 meters. So that's a huge reduction. Your total energy upstream was about less than 15 meters. So you're losing most of your energy within that hydraulic jump.
It's just from the eddy on all the.
Yeah, just from the turbulent eddies. Okay, but that's often a good thing. So like I mentioned, we're often interested in inducing a hydraulic jump because we want the flow to be less energetic, especially if we are discharging water into a natural channel. We want to reduce that kinetic energy as much as possible so that we can limit erosion. So what's one thing that we can do to try to reduce energy even further? Let's say we want to reduce energy as much as possible within our hydraulic jump. What could we add as an engineer to try to engineer our hydraulic jump to reduce as much energy as possible? Yes. Widen the channel, possibly. You mean within the transition, add a
Yeah, that made sense what I said, I'm not sure that's right.
I would have to look into that. let's see, if it's subcritical to start out with and you widen the channel, it would result in an increase in the depth. If it's supercritical starting out, I believe it would actually reduce the depth even further. But interesting idea. Any other ideas for what we could put in to try to reduce energy even more? How would we,
Bumps, and then we put a blocker that makes it go, super critical again, and you put some more blockers.
oh, that's an interesting idea. So you could force it to transition between the critical depth several times. That's a good idea. That's interesting. There's a easier way though, kind of a more conventional way. Maybe think back to the PowerPoint I showed at the beginning of class. Yeah,
You add the sluice gate.
a sluice gate. So let's assume that the flow is already supercritical coming in, and we just want to add something to assist with the hydraulic jump. Maybe thinking back to the pictures I was showing earlier today. Yeah, so we can add energy dissipators to try to assist that hydraulic jump. So let's go ahead and start looking at the case of adding energy dissipators and see what it does to our force balance. So again, we're going to have our hydraulic jump. We have some water coming in that is at supercritical flow. We're going to have some water coming out at subcritical. Within this section here, we're going to get some hydraulic jump. We have our control volume. Oops. And we have our hydrostatic force at the upstream end and at the downstream end. I'm going to call this FH2. This is FH1 at the upstream end. And we have, again, our momentum flux in m.1 times u1. Momentum flux out m.2 times u2. And now let's say we add a energy dissipator into the path of flow. So this energy dissipator, the fluid is going to exert a force on the face of this block. The block is going to induce a reactive force on the fluid as well. So there will be a reaction force from the block. I'm just going to call this F block. And we can actually compute this force analytically using Newton's drag law. So from Newton's drag law, we have that the force exerted by the block on the fluid is equal to the force exerted by the fluid on the block. That's going to be given by 1/2 times the density of the fluid times our drag coefficient times the area of the block's face times the velocity of the fluid squared. And I'm going to use the velocity at the upstream side, u1, as our velocity here. So again, F block, this is the reaction force induced by block. U is our upstream flow velocity. This is the cross-sectional area of the block. And this is our drag coefficient. So all we have to do is add this force to our force balance, which I should have enough time for here. So if we take this force and we add it into our force balance, we will end up with our new momentum equation. We'll have rho times Q times U2 minus U1. So that is the net momentum flux. This is equal to rho times G times our hydrostatic components. This will be H bar 1 times A1 minus H bar 2 times A2. So this part is just our original momentum balance without the block. Then to this, we subtract that reaction force due to the block. So that's going to be 1/2 rho times CD times A block times U1 squared. So very quickly before we break, let's just go back and look at what the block is essentially going to be doing. So the block is exerting a force that acts in the same direction as the hydrostatic force at the downstream end. So basically, the block is acting like there's a deeper depth at the downstream end than there actually is. So what this is going to do is it's going to reduce our depth at the downstream end. I'll take you through an example next class showing exactly how that effect plays out. All right. Remember, I have office hours today at 3, and have a good rest of your day.